Bam! Mr. True, a little birdie told me you were having trouble sketching derivative functions from the graph of a function. Well, my students are struggling with this too, and I'm going to do an extension to a video I did years ago. I'll have a link to that in the description. I think it was this little birdie that told me you were having trouble. And we're going to do 5 more examples of looking at a sketch of a function and trying to draw a reasonable representation of what the derivative would look like. And remember, the 5th example, we're going to work in reverse. We're going to look at the graph of the derivative and try and sketch what the function may look like. Okay, so we're going to look at some settings that are more complicated than I did years ago in my previous lesson. And we have to remember that a derivative tells us the slope of a function. So we're not looking at just the graphs, the function f as a line or a parabola or a cubic function like I did years ago. We're going to go into these more complicated settings, and we really need to remember that. Not just kind of shortcut this process and go, well, he gave me something that looks like a parabola, so the derivative must be a straight line because you're going from a second degree down to a first degree. Well, here we do have a function that does appear to look parabolic in shape, but then when we get to x equals 2, it just branches off and we have a linear function. So maybe this is the graph of a piecewise function. Well, what will the graph of the derivative look like? Number 1, I like to try and identify any points along the function f where the slope, therefore the derivative, is giving us a value of 0. Well, certainly, if we look at some tangent lines here and think about the instantaneous rate of change, we have a horizontal tangent line for this function at x equals -1. So as we sketch a reasonable representation of what this derivative should look like, well, certainly the derivative, which gives us slope, and the slope here is, horizontal, or the function seems to have a horizontal tangent line, you better make sure your derivative goes through the point -1, 0. Now, what happens to the left of x equals -1? Well, the function is falling. And if the function is falling, that means that its slope is negative. So the derivative to the left of -1 needs to be below the y-axis, or the x-axis, giving you or representing that we're getting negative values of y, because one more time, the answer from a derivative is the slope. And it seems to be helping for me to, force my kids to not look at this as one complete picture, but break it down into pieces. So let's say we look here where x is equal to -3. What does it seem like appear that the slope for this graph here is at x equals -3. Well, if I kind of just very lightly dot in what might appear to be a good representation of what a tangent line would be, it seems like at least at x equals -3, that tangent line has a slope of -3 over sort of 1. So at x equals -3, my derivative should be giving me a value of -3. Now, if you say the slope there is -2.5 or -2, I'm okay with that. We're looking for a reasonable sketch of what this derivative may look like. So we're going to be going, and as we go here at x equals -4, the function's falling faster, giving us, which should be showing a more negative slope. And it's negative and it's still falling, so the slope is still negative. It's still falling, but not as fast, so the slope is less negative until, of course, we get to that at x equals -1, where the slope is 0. And then as we move to the right of -1, that function f starts to rise. And of course, if a function is increasing, that means its slope is positive. And it's rising just a little bit, and then it's rising a little bit faster, and a little bit faster, and so on and so on. So that derivative should be giving us, to the right of -1, ever increasing positive values. And if there's some symmetry here, and I've drawn this somewhat accurately, if I were to visualize a tangent line here at x equals -1, maybe we could approximate that slope is, well, my drawing is not perfect, and maybe that wasn't quite -3, but maybe 2, 2.5. Of course, it does look sort of parabolic in shape, so we're going to go ahead and let this derivative the sketch of what a possible derivative would look like continue to go up in a linear fashion, while I'm starting to realize it's helpful to let my kids tell me what the slope is approximately at certain points. We kind of, need this picture to somewhat look neat, of course. And we get to this issue here at x equals -2. Well, at x equals -2, our graph really changes direction and has a sharp bend. Well, don't forget, you can't find a derivative at a sharp bend or at a point of discontinuity. So as we approach x equals +2, at that exact value of x equals +2, at that sharp bend, our derivative is going to be undefined. So you want to indicate with an open dot that at x equals +2, I hope I didn't say -2 earlier, that is undefined. Now, what happens as you go to the right of this sharp bend? Well, we have a linear function. We can clearly see it's just up 1 over 1, up 1 over 1, which means that the slope of this piecewise function, the slope to the right of x equals 2, that stays a consistent value of 1. So I'm going to come down here and remember that derivative tells us slope. I'm going to indicate an answer, a y value of 1, and it's 1 all the way, so our sketch of our derivative should look something to that effect. And that is the sketch of the first derivative. Now, do we have the exact proper, angle, if you will, slant on that oblique section of this graph? Oblique, it's not perpendicular, not vertical. I don't know, but it's a reasonable approximation. If a student, had a line coming through here and maybe just going up to a y value of 3 instead of my y value of 4, 4.5, I'm okay with that. But making sure that we are passing through the x-axis at -1, representing that slope of 0, to the left having those negative slopes, to the right having those positive slopes, having the open dot showing us our derivative is undefined at that sharp bend, I'm good with that. Now, if I want to draw another step of that derivative, if this is f, and if this really indeed is a linear function, it seems like for this portion of the graph over here, our slope is a little bit less than 2 over 1. So the slope of this derivative, this first derivative, to the left of x equals 2 seems to be a consistent, let's say, almost 2. So I'm going to have it just below that y value of 2. It's still undefined here, and you can't take a derivative at a point of discontinuity, so I'm going to keep that open dot there. And to the right of x equals 2, we have a horizontal line. So the slope of a horizontal line is 0. So our second derivative is going to look like this. So actually, I just did 2 examples there in one. Over here, I got a function f, which has a vertical asymptote at x equals 0. And way over here at x equals -2, 4, 6, 8-ish, unless I miscounted, it seems like, look, that graph is almost horizontal. It's just staying above the x-axis and rising very, very slowly. And let's see. I don't really have a set of markers like I would in my class, but we have a tangent line which has a slope nearly 0. We have a tangent line which is got a slope of, I don't know, maybe 1-ish, a little bit less than 1. I have a tangent line whose slope is, let's say, maybe +3. I have a tangent line whose slope is maybe +10. And that function that was almost flat, having a slope of almost 0, but rising, the x-axis is acting as an asymptote, starts to shoot off to infinity as we approach x equals 0. So that slope is getting ever and ever greater, approaching infinity. So our first derivative here, let's keep it in orange like our first example, maybe looks something like this. I'm going to pull it apart just so you can see the difference between the orange and the white. Again, this is a reasonable sketch of what the derivative may look like. I'm not claiming it to be 100% accurate. But that function is increasing, giving us, of course, positive slopes until we go vertical, and that slope is approaching undefined. Now over here, though, instead of rising and shooting off to infinity, it's like as soon as you get past that asymptote, boom, it's falling very, very quickly, meaning we have very, very negative slopes. Very, very negative. So maybe like at 0.5, that slope is like -10 or something like that. But that starts to, and it's to the right of this asymptote, that graph never stops falling. And if the graph is always decreasing, your derivative is always negative. So you better make sure your sketch stays below the x-axis. But you can see it's flattening out, and as you have this graph flatten out and start approaching the x-axis as an asymptote, the slope really never becomes 0, but it does approach 0. And so this is our sketch of what f prime, the first derivative, may look like. And it, just make it a reasonable sketch. It is always increasing as x approaches 0 from the left, and this function is always decreasing. So we have those negative slopes as you approach 0 from the right. So let's move on to our next two examples. So for our third example, we've got this sort of wavy function thing going on here. Okay, well, that looks rather complicated. How are we going to sketch, oh, and this is, I didn't label it, but this is some kind of function, not f prime, but this is some kind of function. And we're going to sketch its derivative. Well, like I like to do in my class, let's highlight, it's kind of the easy points, if you will, or the key points. Like maybe I see a point and I go, maybe that slope is negative, whatever, -3, but it's really -2.5, something like that. There's a little bit of room for error, but look, man, there is a horizontal tangent line right there. So at 3 pi over 2, this function, its slope is equal to 0. So we better make sure that our derivative passes through that point. And like here, we have a horizontal tangent line. So let's make sure our derivative is giving us that answer of 0, that slope of 0. And as well here, and as well here. Okay, now I kind of cheated here a little bit. I did not include some graph paper grid, which I get from my handy-dandy grid chalk maker thingy-majiggy. But at any rate, because of the scale being this pi over 2, pi 3, pi over 2, and so on, and pi being, 3.14 approximately, yada, 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 and the vertical scale is 1. So what's happening? Well, what's happening between this horizontal tangent line, which has a slope of 0, and this horizontal tangent line with a slope of 0? Well, between negative pi over 2 and positive pi over 2, this function is rising. Well, if the function's rising, it has a positive slope. Therefore, the derivative had better be giving you positive answers. And where between negative pi over 2 and positive pi over 2 is this function rising the fastest? Where does it seem like it's giving us the biggest answer for the slope? Well, it's right there. Because, and forgive my drawing, I'm not a computer, but it's rising slowly just a little bit to the right of negative pi over 2, and it's rising quicker and quicker and quicker. And we have sort of this greatest, I see sort of like a most steep, or the steepest slope here at x equals 0, and then it kind of starts to come over. Well, that's because we're going from concave up to concave down. At x equals 0, we actually have a point of inflection. So at that steepest visual slope, let's make sure that our derivative is giving us the largest possible answer. And it doesn't really look like a slope of 1, but I kind of happen to know that that one is. So between negative pi over 2 and positive pi over 2, it has a slope of 0, rising slowly and faster and faster and faster, and then that slope starts to decrease. So our derivative is going to look something like this. But I think someone's at my door. Let me come right back. Alrighty then. So to finish this up, yes, 0, 0, and rising all the way, having that derivative giving us positive values. Between this x value of 0, slope of 0, and between this slope of 0, our function is falling. And like over here, instead of rising its fastest rate, we have its most negative slope. So this, at this point here, where we go from being concave down to concave up, our derivative is giving us our smallest value. And I just happen to know that that's going to be equal to -1. And so as we kind of connect the dots, oh, nope, our function's rising again, and so on, we get 0 and 0, our slopes, our function falling from -3 pi over 2 to -pi over 2, and here it's falling at its fastest rate, so falling means slopes which are negative. We get the graph of our first derivative. So this is our f prime of x. Now, did you notice a pattern between the white graph and the orange graph as I was drawing that? I hope so, because that means you know your unit circle. This is f of x, as it turns out, happens to be equal to the sine of x. And this orange graph happens to be, well, what does it look like? At x equals 0, the function is giving us a value of 1 at pi over 2. That function is giving us a value of 0 at pi. This function is giving us a value of -1. Actually, this derivative function, in case you never really connected the dots before, and that's not really drawn correctly, let me just change that a little bit, is the cosine of x, right? The derivative of sine is cosine, and there you can see it graphically. Over here in our fourth example, we have some kind of root function, and this function at -2, 4, 6, 8 or so, -9, whatever, but we have an x-axis here that is acting as a horizontal asymptote again, like our previous example before, and this function is rising, but very, very slowly. So back here at, I counted this, but now it's bothering me, I forgot it was, -2, -4, -6, -8, at -9, our slope is just barely positive. This function is increasing, but very, very slowly. Well, okay, and it's increasing a little bit faster, and it's increasing a little bit faster, giving us more and more positive slopes. Maybe the slope here is equal to +1, but then it goes very vertical between the x value of -1 and the x value of 0. And actually, I was trying to draw this as if there was a vertical tangent line at x equals 0. So the graph of this derivative from this function f is barely increasing faster and faster, and really going vertical, saying that our slope is, of course, the slope of a vertical line is, it's not an asymptote like our previous example, but the slope of a vertical line is undefined. We're approaching a slope of infinity, right? You cannot find a derivative. You can't find the slope of a vertical line, or you can, you can say it's undefined. And then just as you pass the other side of x equals 0, you get to the right of that vertical tangent line. That graph is still increasing very, very rapidly, and then slows down and starts to rise very, very slowly, meaning the slope, right, this is concave down, and when a function is concave down, that means the first derivative is decreasing. But this function, while starts to lay over and act like there's a horizontal asymptote out here somewhere, this function is never going to stop increasing. It just increases very, very slowly. So just to the right, very large values for the slope. We need to, as far as the derivative is concerned, see that there is a vertical asymptote at x equals 0. There's not an asymptote for the original function, but for the derivative. And then we come down here and make it look something like that. That is a reasonable, that orange graph is a reasonable sketch of what the first derivative would be for this function. And again, I want to focus on the graph of the function, not necessarily giving you the equation of the function, having you find algebraically the derivative of that function and then graphing it with a graphing calculator. I want you to see it and draw that reasonable sketch from a graph, and just using your knowledge, of the fact that a derivative is just simply giving you that slope. I got one more example coming up right now. Okay, so we have, I basically drew a parabola. But this time, I drew it in white, but then I realized all my derivatives were in orange for the previous 4 examples, so let's be consistent. I have a derivative. So we're going to look at the graph of this derivative and try and sketch what would be a reasonable approximation of what the antiderivative, or basically function f, is going to look like. Well, one more time, right? Derivatives give us slope. And what is this derivative telling us about the original function? Well, it's telling us that x equals -3 and at x equals +3, make a big old dot, kind of blur that over a little bit, that the slope, a derivative tells us slope, and the answer we're getting from this derivative is 0. So our original function on, okay, now maybe, well, I could have our function go through there, except that I don't want you to think that the values from the derivative are the values from the function. So the original function could go there, f could go through there, but we better make sure that our function that we're about to draw has a horizontal tangent line, has a slope of 0 at -3 and +3. Now what's happening between, see, I kind of wanted to mark these as sort of like important points, so let me do this. Here we go. Between those two markers, our derivative is obviously giving us negative values, which means that between -3 and +3, our function that we're about to draw had better be what? Decreasing, because our slopes that we're getting from the derivative is negative. So, I don't know, here. So I'm going to kind of visualize a horizontal tangent line here. And I'm going to visualize a horizontal tangent line there, and I just hit my mic, so I hope that static sound wasn't too bad on the mic. Between here and here, my function needs to be falling. We need to have horizontal tangent lines. And actually, if we can approximate a tangent line who has a slope of -3, that would be even better. So if I, maybe here, 1, 2, 3, okay, some falling. Maybe I want to drop that down a little bit more. Again, it's just a reasonable sketch, but so I want for a period of time to have a tangent line which looks like it's sort of got that -3 slope, but 0 slope, 0 slope, most negative slope in the middle, and all negative values from the tangent, all negative values from the derivative, so our function needs to be falling, something to that effect. Now, what happens to the left of -3? Well, the answers that we are getting from our derivative are all positive, and if my derivative is giving us positive answers, then our function needs to be increasing, right? If the function is increasing, our derivative is giving us slopes which are positive. And it's got back here a very large value from the derivative, so a very positive slope, very fast increase, or increasing function. And it's going to look something like this: a little bit positive, more positive, more positive, more positive, more positive as far as it's increasing. So it's increasing slowly, it's increasing faster. Of course, it seems weird because I'm doing this in reverse because I just want to make a smooth graph. It's increasing very, very fast. So let's try and visualize this again. So we have a function that's increasing, and increasing very steeply, giving us very positive values of slope. And it's increasing a little slower. Chalk down! It's increasing a little slower. It's not increasing. The slope is 0. And then to the right of x equals 3, we go from a slope of 0. Now this is going to kind of flow a little better because I'm going off to the right of the graph. But slope of 0, horizontal tangent line. Slope of +1, so it's starting to, whoops, that's orange, starting to swing up, and those slopes that we are getting ever bigger as x increases. So as we swing to the right, this function needs to be increasing, faster and faster and faster, because the slopes we are getting from the derivative are, greater and greater. So this would be may be a good approximation of what f looks like. Now, that's not the only good approximation for the graph of f. And by the way, when you take the derivative of a cubic function, you get a function with a degree of 2. So I've drawn what looks like a cubic function, a third degree, and indeed the derivative appears to be sort of like a second degree parabola. But what is if I say f of x is equal to 3, and I ask for f prime of x, or say, if I just say, well, I have a value of 3, what's the derivative with respect to x of 3? Well, that's going to be 0, right? And when you take a derivative of a constant, it just kind of goes away. So when we learn, we haven't learned it yet, but when we learn how to integrate, these constants are effectively like vertical shifts. Like way back in pre-calc, if I say that we have f of x is some kind of function, sketch f of x plus 3, you would just take that original parent function and shift it up 3 units. Well, when you take the derivative of that constant, it's 0. When you go to integrate, it's like there's nothing there. So what I'm trying to get across is I could basically now take this sketch of my cubic function and just move it up and down anywhere I like, and it would still be a reasonable sketch, because if there was a vertical shift, after you take a derivative, it goes away. You don't know what that vertical shift is. In other words, I can say, hey, at x equals -3, make sure I have a horizontal tangent line. At x equals +3, make sure that slope is 0. Make sure that you're visualizing kind of like a horizontal tangent line. Hey, the derivative is negative between these two values, so between -3 and +3, make sure your function is falling. To the left of -3, your derivative is giving you positive values, so make sure your function is increasing. To the right of 3, our derivative is giving us positive values, so make sure to the right of 3, your function that you're trying to sketch, f, is rising. Either one of those sketches of what may be our antiderivative of f prime of x, effectively just an idea of what f may look like, is acceptable. Because, through the derivative process, we lose that plus constant, we lose that vertical shift. I hope this helps you now understand how to take the sketch of a function, or even a derivative, and come up with a sketch of, say, a second derivative, or in this case, the antiderivative, function f from f prime. So it's challenging. I hope this helps you see how to give these sketches, get these sketches done with a little bit more accuracy. I'm Mr. True. Bam! Go do your homework.